Okay, the first thing I'll do before I start today is show you a quick breakdown of the exam results. So this is our normal Tuesday activity of looking at different metrics and different study habits and things and talking about them. So since we had our first exam last week, here's a breakdown of the results. So I mentioned the average was a little bit higher this semester than previous semesters. You can see how much higher it was, 0.4 out of 20, which is about 2%. So our average was in the C+ range this time. A little bit bigger deviation, but that's because we're a smaller class, so it's natural to expect more of a spread in scores in terms of standard deviation. The high score was 19 out of 20. 5 students achieved that. Nobody was able to crack the nut and get a perfect score, but we had a lot of good scores overall, with the most popular being 16 out of 20. So I think overall the results are fine. Obviously, you know, your mileage may vary depending on how you did individually and how you feel about this, but as we talked about, just you know, if you need to improve your scores, there's time to do that. You just have to change your habits and talk to me about how to do that. If you're happy with your score, that's great, but you realize that the exam scores they tend to get lower as the semester goes on, so you're going to have to keep up or even increase your effort to maintain where you are now. All right, so that's kind of a rundown of the first exam, and let's get right into what we're going to talk about today. So if you'll recall, we ended with last time, we had started chapter 5, which is all about moles. Moles is kind of the major theme of that chapter, and we talked about both the definition of a mole as well as how to use it in sort of determining the composition of a compound and how it's related to that. So what we ended with last time was using the chemical formula of a compound to determine the mass percent. So now that we have this relationship between mass and moles, we can do that. We can take the formula, which is a mole ratio of all the elements in the compound, and then convert it into mass ratios or mass percents. It's pretty straightforward. What we're going to do today at the start is do the opposite. We're going to talk about how to take the mass composition of a compound, either in terms of absolute mass or mass percents, and then convert that back into a chemical formula. But before we start that, we have to realize something about this, which is that if you just have the mass composition of a compound, you cannot uniquely determine what's called the molecular formula. You can only determine the empirical formula. So let's understand the difference between those before we get into it. So the molecular formula is the total number of each atom in a molecule of the compound. So it's the total number of each atom in a molecule of the compound. So it's most relevant to covalent compounds, which we think of as being composed of molecules. And it doesn't necessarily have to be the smallest whole number ratio. So when we talked about the nomenclature and formulas of covalent and ionic compounds, we saw for ionic compounds we always put things into lowest whole number ratios. For covalent compounds, that's not necessarily the case. The formula of a covalent compound may or may not be the smallest ratio of the elements, and so the molecular formula tells us exactly how many of each atom is in a molecule of the compound. Now, the empirical formula would be that lowest whole number ratio, which, again, for a covalent compound doesn't give us a whole lot of information other than the relative number of moles of each element. But at the same time, as we said, when you're given mass percent or mass composition, this is all you can determine is empirical formula. All right. Now, it's important to recognize that for ionic compounds, specifically binary ionic compounds, some of the ones with polyatomic ions, this may not 100% be true, but typically in ionic compounds, the empirical formula is the same as what we would say is the ionic formula of that compound. Because as we talked about for ionic compounds, you're always trying to get the smallest whole number ratio. Again, it's always going to be true for binary ionic compounds, which are just 2 elements. If you have polyatomic ions involved, that may or may not be the case, but it's in general going to be true for ionic compounds, that your empirical formula is just the formula of the compound. But for covalent compounds, very often, the formula of the compound, the molecular formula, is not the same as the empirical formula. So here's some examples of how you sort of the relationships between molecular formula and empirical formula. So if we're looking for the greatest common factor in these subscripts. Remember, the subscripts tell us the number of atoms in each molecule or the number of moles of each element in 1 mole of that compound. It can be interpreted in 2 ways. And we look for the greatest common factor. So if we have N2H4, which is a compound called hydrazine, we can see that there's a greatest common factor of 2. We can reduce this. So if we divide the whole thing by 2, we will get an empirical formula of NH2. So the molecular formula is N2H4. The empirical formula is the smallest ratio of those 2 elements, which would be NH2. In water, H2O, we can't reduce it any further because we have a coefficient of 1 and there's no common factor between those 2 that would leave it as whole numbers. So this is going to be just, in this case for water, the empirical formula and the molecular formula are the same. So that is possible. It's not always the case that they're different. So if you cannot reduce it to any smaller whole numbers, then your empirical and molecular formula are the same. Empirical formulas are always whole numbers, so that's another important point that we should keep in mind as I gave in the definition. C6H6, so one compound that has this formula that we talked about, I think last week or the week before, is benzene, that sort of hexagonal cyclic molecule with delocalized electrons that we discussed briefly. So it has a formula of C6H6, and when it's empirical formula, we see that there's a greatest common factor of 6 there. So we can divide the whole thing by 6, and the empirical formula would be much more simply stated as just CH, one of each. And then finally, B3N3H6. This compound has the greatest common factor of 3. You can divide all those subscripts by 3 to get smaller whole numbers. And then this would be BNH2. Come on. Let me try to reset this sometimes. Okay, now reset. All right, there's some weird timer on the lights here that it wrestles control the lights from me when I don't want it to. But anyway, so that's the relationship between molecular formula and empirical formula. The molecular formula is always some multiple of the empirical formula, some whole number multiple. So again, to convert between them, we divide by the greatest common factor. So that's kind of how we define it. So let's then talk about the steps then for determining the empirical formula of a compound if we are given mass compositions. All right, so the way we're going to do this is, hang on a second. All right, so what we're going to do is we're going to have masses of each element, or mass percents, and we'll talk about the slight differences involved with those. But we're going to convert the mass of each element into moles. Okay, because remember that the formula of a compound is the mole ratios of the elements. So if we have the mass of each element, we can convert it to moles. And remember, the way that we do that is using the atomic mass. Okay, so the atomic mass of an element can be thought of as the number of grams of that element in 1 mole, so we have that relationship to convert between mass and moles. So then once you have moles of each element, we need to get the smallest whole number ratio of those moles to get the empirical formula. So the way we do that is we're going to divide each of those moles by the smallest one. So we have a number of moles for each element, and we're going to divide all of them by the smallest of those numbers to reduce one of them to 1, and the rest will be then relative to that smallest one. And again, we're going to demonstrate all these steps, so it'll become more clear as we illustrate them. But just sort of writing them out at the start to keep track of our process. All right, so you have a molar amount, a molar quantity for each element, and you divide all of them by the smallest of those to reduce it down to a ratio. Now, what is sometimes going to be necessary, I don't think it comes up in any of the example problems, so I'll illustrate it here. This is an if necessary step. You're not always going to have to do this. Sometimes you'll get fractional subscripts for some of the elements when you do this. They're not always going to come out to whole numbers after this second step here. So in that case, you'll need to multiply the whole thing by a small whole number to make all of the subscripts into whole numbers themselves. All right, so some of your subscripts after that second step are going to be fractions, or more likely written as decimals, the way they'll calculate it. So then you have to make sure that you turn them into whole numbers. And multiplying the whole thing, you can't just multiply one number. You have to multiply all the coefficients by the same factor to keep the ratio the same. And in the, one sort of warning that I'll have about problems like this as we go through it, I'll sort of point it out when it's relevant, is you don't want to do too much rounding in these types of problems. So if you do steps 1 and step 2 and all the numbers you get are like really close to a whole number, like something 0.9 or something 0.05 or less, like if it's really close to a whole number, go ahead and round it. But if it's not that close to a whole number, you don't want to round, you want to make sure that you multiply by an appropriate factor. So here's some examples of this last step in action. So let's say we do these first 2 steps and we get this formula here, C0.5H. Okay, so we don't want to just round that 0.5 up to 1. That's way too much rounding for a problem like this. So if you get anything 0.5, then you want to multiply by 2. So you're going to multiply the whole thing by 2, so both subscripts multiply by 2, and you'll get CH2 as the correct empirical formula. All right? Or let's say we got C, and then we got H. This is not a real empirical formula, but we'll just go with it. So we got CH1.667. Again, the temptation is just to round that to 2 and say, oh, that's also CH2, but that's too far away from the whole number to do rounding. Again, unless it's like 0.9 something, you'll round up, or 0.1 maybe you'll round down, but if it's further away from that, then you want to try to adjust it by multiplying by a small factor. So if you see anything 0.333 or 0.667, you should automatically think of 3 as the factor you multiply by. So if we multiply that whole thing by 3, we would get C3, and then H should be 5, I believe. I did that right. Yes, 5, okay. So you'll multiply both subscripts, both coefficients in that, by the same number. So 1 times 3 is 3, 1.667 times 3 is 5. That takes both of them into whole numbers. So again, don't do too much rounding in these problems unless you're really close. And we'll set up the problems in such a way that if you don't need to round the numbers after the first 2 steps, it'll be obvious. So just follow the process. Don't do too much intermediate rounding. Keep at least 1 or 2 decimal places in all your numbers to make sure that you're not truncating them too much along the way. But if you do it correctly, it'll be pretty obvious whether or not you have to do this last step. And I don't think this last step comes up in any of the examples I give today, but it will from time to time show up. So it's important to remember it. All right, so let's just do some examples to see how this works. So one variation in this type of problem is that we just give you the masses of all the elements in the compound. So if we have this compound here, vanadilyl chloride, it's an orange liquid, sort of a rare metal compound that exists as a liquid. And we find that, we analyze this compound and find that it has 1.47 grams of vanadium, 0.462 grams of oxygen, and 3.07 grams of chlorine. So it has those 3 elements in it, those mass amounts for a given sample of this compound. What is the empirical formula? So the steps in these problems for determining empirical formula are always going to be very similar to one another. We're just going to convert the masses into moles. For each element, we have to do this. So we have 3 elements in this case. So for vanadium, we're going to find the moles of that, which is atomic symbol V. It's 1.47 grams of that element. That's our given number. Then we're going to use the atomic mass to convert into moles. So we want moles on the top, grams in the bottom, and the relationship between grams and moles, as we said, is the atomic mass. So let's load our periodic table and look what that is for vanadium. All right, so vanadium is here, atomic number 23, and the number below, which is the atomic mass, is 50.94. So that's the number we're going to use to convert mass to moles for vanadium. So 1 mole of vanadium has a mass of 50.94 grams. So that's what we divide by to convert mass to moles. Grams cancel, and then we get 0.0288 moles. We're going to do the same thing for the other 2 elements. So for oxygen, there's going to be 0.462 grams. And we're going to divide by its atomic mass. The atomic mass of oxygen, I don't want to go back to the periodic table a million times, but that's 16 if you find it on the periodic table. So we divide by 16 to get 0.0289, so almost the same number. So we would conclude that there's the same number of moles of V and O, vanadium and oxygen, in the formula. Then we do the same thing for chlorine. So its mass is 3.07 grams in this compound. And the atomic mass of chlorine from the periodic table was 35.45. Again, all these atomic masses you get straight off the periodic table. We're doing it for elements, so we just have to read them straight off. And we get 0.0866 moles. All right, so then the last step is going to be to divide all of these by the smallest number to get them into a whole number ratio. So our formula could technically be written as this: V 0.0288, O 0.0289, Cl 0.0866, but of course we don't write chemical formulas or empirical formulas with decimal subscript. We always have whole number subscripts in either of those. So what we're going to do is divide all these by the smallest one. So the smallest of those is 0.0288. So all those numbers are going to get divided by that. And again, it might not come out exactly to whole number ratios, but that's going to be a 1.0288 by itself. 0.0289 divided by 0.0288 is pretty darn close to 1, so it's going to be VO. And then for Cl, that number divided by 0.0288 is very close. I don't know if it's exactly 3, but it's very close to 3. So VOCl3 would be the correct empirical formula, writing those ratios as small whole numbers instead of as decimals as they originally come out. All right, so any questions on that process? Again, these types of problems in this course, you just have to learn the steps, practice them, and it'll all become second nature eventually. All right, let's do another one that's slightly different here. So what is the empirical formula for a binary compound consisting of boron and fluorine that is 15.94% boron by mass? All right, so there's a couple of key differences here. So one is that we didn't give you grams of elements, we gave you a mass percent instead. And also, we only gave you one of them. We didn't give you the percentages for both. So how do we deal with this? So the first thing to realize is, again, remember the definition of binary compound. That means it just has two elements in the formula. And from stuff we learned about way at the beginning of the course, if you have mass percents of elements in a compound, they will all add up to be 100 when you sum them all up together. So we're giving you the mass percent of boron. We don't have the mass percent of the other element that's fluorine, but the sum of those two should be 100. So to find the mass percent of the other element, fluorine, we have, it's just 100%, which is the total, minus the mass percent of boron. So that's total. That's your boron mass percent. There's only two elements in the compound, so subtracting those gives us the percent of the other element, fluorine. Okay, so this compound is 15.94% boron by mass and 84.06% fluorine by mass. So now we have mass percents for both elements, but how do we deal with those? Because these are not mass amounts like we had in the last problem, these are percentages. But remember that the mass percent is a composition, a measure of composition, which is going to be true no matter how much of that compound we have. Again, whether we have one molecule of that compound or whether we have a whole huge pile of it, the mass percent will still be 15.94 and 84.06. So we can assume whatever amount of compound we want and still use these percentages in the same way. So the convenient one for mass percent is to assume that we have 100 grams of the compound. Because if we have 100 grams of compound, then the mass of each element is just equal to the percentage of that element. Because remember, percentage is amount out of 100. So if we assume 100 grams of compound, we'll have 15.94 grams of boron and 84.06 grams of fluorine. That's what those percentages mean. So then we can just take those numbers and convert them into moles and follow the same steps as the last problem. So for boron, we start with its amount, which is 15.94 grams. That's how much boron there would be in 100 grams of the compound. And we're going to divide by the atomic mass to convert that into moles. So from the periodic table, again, we look up atomic masses from there. Boron is 10.81, fluorine is 19.00 to 2 decimal places, which is plenty. Okay, so we need those two atomic masses, so it's going to be 10.81 for boron. And so when we divide that, we get 1.474 moles of boron in 100 grams of compound. Then we do the same thing for fluorine. So the mass percent of fluorine was 84.06, which again means there's 84.06 grams of fluorine in 100 grams of compound, and we convert to moles by dividing by its atomic mass, which is 19.00. So 4.424 moles of fluorine. All right, so again, those are the moles of each element in 100 grams, but we want to write the chemical formula, or the empirical formula in this case, as smallest ratios. So we start with those two amounts, which are clearly not whole numbers, and we don't want to round them because they're not very close to whole numbers on their own. So that's 424. Then we divide both of those by the smaller of the two, which is 1.474. And again, we don't need to do any additional factoring here because it's just going to come out to BF3 directly or very close to that without any additional operations required. All right, so it's the same set of steps. We're just using the percentages and interpreting them as masses out of 100 grams in this case. So it works really the same way. Okay, so any questions so far? So that's how we get the empirical formula. If we want to get the actual molecular formula of the compound, there's one key piece of missing information that we need, which is the molecular mass of the compound. Okay, so the mass percentages or the mass composition, however it's given to you, as we said before, that can only get you to the empirical formula. But if you want the molecular formula, there's one more piece of information you need, which is the molecular mass. So if we give you the molecular mass in a problem, that, along with the empirical formula, will allow you to determine what the molecular formula is, because the empirical mass, which is the molar mass of the empirical formula, is going to be related to the molecular mass by some small whole number multiple. So we just have to figure out what that multiple is. We multiply the empirical formula by that factor, and that will give us the molecular formula. So again, this is best learned with an example. So let's say we found an empirical formula of CH2, and being in the, oil and gas capital of the United States, there's hundreds, if not thousands, of petroleum compounds that have the empirical formula CH2. So if you want to figure out what the actual molecular formula of that compound is, there's going to be, again, many compounds that have that empirical formula. But we're telling you here that the molecular mass is 70 grams per mole, or AMU, whatever unit you prefer. So we want to figure out what's the molecular formula with those two pieces of information. So as I said, what we'll usually do, and we're going to piece that together here in a little bit, you're going to use mass percentages or mass composition to get your empirical formula. We're going to give you the molar mass of the compound, or the molecular mass, and then you're going to use those together to figure out what the correct molecular formula is. So what you need to do in this case is you need to find the empirical mass, which is, again, the molar mass of your empirical formula. So if we have CH2, the empirical mass is going to be, we have one carbon, and we need the atomic masses of each. So we have carbon and hydrogen. Carbon is 12.01. Hydrogen is 1.008. So adding those together will give us the empirical mass. So one carbon with an atomic mass of 12.01. I chose AMU here, but again, you can think of this as grams per mole. Their numbers are the same. So that's carbon, and our empirical formula has two hydrogens. So 2 times the atomic mass of hydrogen, which is 1.008. And we don't need to be super precise with this because we're only giving you the molecular mass to, 2 figures here. So we can just say that's about 14 AMU. All right, so our empirical formula has a molar mass of 14 AMU. Our molecular mass is 70. So then what we do is we divide the two to figure out the factor that relates the empirical and molecular formula. So if we take the molecular mass divided by the empirical mass, we have 70 AMUs is our given molecular mass, 14 AMUs is the empirical mass that we calculated, so that comes out to 5. So what this means is that our molecular formula is 5 times the empirical formula. So CH2 is our empirical formula, we multiply the whole thing by 5, and that gives us a molecular formula of C5H10. So again, one of many compounds that would have the empirical formula CH2, in this case is C5H10. Okay, so that's how we're going to approach that. We need just one additional piece of information that's going to be given to us, and then the relationship between molecular mass and empirical mass will also be the relationship between the empirical and molecular formulas. All right, so that's how that works. So let's put it all together then in one big example problem that combines pretty much everything we've covered so far today. So we have a compound that has 28.18% mass Mn, which is manganese, 30.80% carbon, and 41.03% oxygen, and it has a molar mass of 389.98. Determine its molecular formula. So this is a pretty standard type of problem, where in this case we're not just determining the empirical formula, we're actually going to go to that additional step to get the molecular formula. And the steps are going to start out the same. The first thing we have to do is find the empirical formula, so we're going to follow the steps that we've already learned. These are given as percents, so we're going to assume 100 grams of the compound, which means that the elemental percentages are just the mass of each element in 100 grams. So if we want to do this for manganese, we find the moles of each element. We'll start with Mn. It's 28.18 grams. Then we divide by the atomic mass to get that into moles. All right, so we're going to need atomic masses. So again, that always comes from the periodic table. Mn is there, 54.94. We also have carbon and oxygen, which are 12.01 and 16, two numbers we've seen a lot. So manganese is 54.94. That's the first number we're going to use to find its molar amount. And so we get 0.5129. All right, again, it's helpful in these problems not to do too much intermediate rounding. So we'll usually give you mass amounts to 3 or 4 significant figures. Keep at least that much in these intermediate steps, because we're still not close to done yet. So don't do too much rounding. Don't just round this to 0.5. Keep some of those extra decimal places to make sure that you don't do unnecessary rounding that's going to cause your answer to be off a little bit. For carbon, we'll do the same thing. It's 30.80% carbon. So we have a 30.80 grams of carbon. We just divide by its atomic mass, 12.01, to get 2.564 moles of carbon, and then we do the same thing for oxygen. 41.03 grams. .564 moles of oxygen. Okay, so we have moles of each element now. So we have what we need to get the empirical formula. I'll lop off one figure here just to make it easier to write, but we can keep all of them if we want. We have Mn 0.513, carbon 2.564. These are the moles of each element, but again, they're all decimal numbers, so we have to divide to convert them to whole numbers. We divide all of them by the smallest, which is 0.513. And what we get is MnC5O5. Now, it's entirely possible that this is also the molecular formula of the compound. Again, the empirical formula and the molecular formula can be the same. But we don't want to assume this is. We have to compare the empirical mass to the molar mass to figure out if we need to, in fact, multiply this by a factor to get the molecular formula. So that's going to be the next step. I left a little bit of extra room for myself for work, because I knew this problem would probably take up more than one page. So hopefully you guys have enough space where you're writing. And what we need to find now is the empirical mass and compare it to the given molar mass. So what we're going to do is we're going to take this formula, MnC5O5, and figure out the molar mass that corresponds to that formula. So for manganese, we have 1 in the formula, and it has 59.94. If you'll excuse me, I'm going to leave out units for now. Let's not do that. That's sloppy. All right, 54.94 grams per mole for manganese. We have 5 carbons, which have an atomic mass of 12.01. And then we have 5 oxygens, which have atomic masses of 16.00. So our total empirical mass is 195 grams per mole. So then to figure out what we now have to do is we have to compare the empirical mass, which is 195, to the given molar mass, which is 389.98. So those are clearly not the same, which means that our molecular formula is some multiple of the empirical formula. They're not the same in this case. So we divide the two to figure out what factor we need to multiply our empirical formula by. So the molar mass divided by the empirical mass. So this is given 389.98 grams per mole, and we divide that by the empirical mass, which is 195.00, and to a good approximation, this equals 2, probably like 1.999 or something like that, but it's essentially 2. So that means our molecular formula is going to be our empirical formula, which we found up here, doubled, which is going to be Mn2C10O10. So that's the last step to get the empirical formula and convert it to the molecular formula. Okay, so if we ask you for the molecular formula, make sure you follow this last step, and to do that you will need to be given the molar mass, which will be provided to you. Experimentally, if you're curious, there are techniques that allow us to measure the molar mass of a compound pretty accurately, so that in combination with the elemental percentages can give us the molecular formula like we did here on pen and paper. Okay, any questions on those steps? So that's probably everything we need to know about determining the formulas of compounds for now. All right, the next variation in all of this is going to be another method we have for determining chemical formulas, and again, in reality, empirical formulas, which is combustion analysis. So this is just a slightly more complicated way of doing it instead of giving you the direct percentages of elements. Now you might ask, well, what's the point of doing it this way if it's harder? Well, this is because experimentally, it's hard to just take a compound and just break it up into its elements and figure out, okay, I have this much manganese, this much oxygen, this much carbon, we're good to go. There's not really a lot of experiments that allow you to do that easily for most compounds. But what you can do for a lot of compounds, especially organic compounds, things that have a lot of carbon, hydrogen, oxygen in them, is you can burn them. So you set them on fire. And then when you set them on fire, that organic compound converts into carbon dioxide, water, and if there's any other things besides carbon and hydrogen and oxygen, you'll get other stuff out as well. Okay, so then what we do with combustion analysis is we burn the compound, we measure the mass of CO2 and water that form, and we use that information to figure out how much carbon, hydrogen, and oxygen is in the original compound. So we're going to use the CO2 to find the mass of carbon in the compound. We're going to use the H2O that forms to find the mass of hydrogen. And then if there's other stuff in the compound, so we can always get the mass of carbon and the mass of hydrogen, or the moles of each, using how much CO2 and water forms during the combustion reaction. But then if there's other stuff besides carbon and hydrogen, that's going to be found by difference. So this is going to be found so we know, so what you do is you subtract the amount of carbon and the amount of hydrogen that you find from the mass of compound. So when you do an experiment like this, and this is done, this is not like one of these archaic things that we teach you from hundreds of years ago. People still do this today to find out compositions of their compounds. You mass out your compound very accurately, so you know how much mass of compound you're starting with. You set it on fire, you burn it. So hopefully it's not too valuable because you don't get it back. So you burn it and you measure the mass of carbon dioxide that forms. You measure the mass of water that forms, and if there's anything else in the compound, the difference between the mass of the compound and the mass of carbon and hydrogen will give you what else is there, at least in terms of its amount. Okay? So this allows us to determine the empirical formula of an unknown compound. So this is a pretty general technique for doing that. Again, especially relevant to organic compounds, which burn and are mostly composed of carbon, hydrogen, and oxygen. All right, and what you're hopefully starting to see in this part of the course, we're talking about different ways of finding the formula of a compound, determining the chemical formula, and there's not one magic bullet technique that just gives it to you. Like you guys watch shows like CSI where they just like put everything into a machine and it spits out the answer in front of them. It's not quite that simple to determine almost anything in science, especially the formula of a compound. So there's a lot of different techniques we use in combination, and combustion analysis is one of them, which in certain situations is very valuable. All right, so let's talk about how this works then. So I don't think your book actually covers this, but there are still homework problems on it, so I want to make sure you know how it goes. So the way you do this again is we're going to tell you what elements are in the compound. You at least have to know that to start. So if we have a compound with carbon, hydrogen, and bromine, then we burn it. So we take 5 grams of the compound, and when we burn it, we produce 0.871 grams of carbon dioxide, 0.179 grams of water. What is the empirical formula? Again, since we want the empirical formula of the compound, we need to be able to figure out how many moles of each element there are. Now, if the compound only had carbon and hydrogen, we could do a series of conversions that takes the mass of CO2 and the mass of water and figures out how many moles of carbon and how many moles of hydrogen are in there. So that would be one less step. But in this case, we also need the mass of carbon and hydrogen. So we have to use that to figure out how much mass of bromine there is, which is the other element that's present in this compound. So we're going to start by finding the mass of each element. And so for the mass of carbon, we start with, we burn the compound, and we remember that all the carbon that's in the compound originally ends up in CO2. So we have that much CO2, all of our carbon that we originally had is in there. So we have to figure out how much carbon is in 0.871 grams of CO2. Now there's a couple different ways of doing this, but the series of steps that I like to follow is, let's first figure out how many moles of CO2 that is. So this time we need to use the molar mass of CO2. I didn't give that to you here, but the molecular weight or molar mass of CO2 is going to be carbon is 12.01, 2 oxygens, which are 16, so that's going to be 44.02. So that's the molar mass of CO2, so we can use that to figure out how many moles of carbon dioxide there are. All right, but this is moles of CO2. What we want is moles and grams of carbon. But remember that the chemical formula, CO2, tells us the relative number of moles of each element in that compound. So from the formula, we have 1 carbon. There's no subscript on carbon, so that means we have 1 mole of carbon for every mole of CO2. We could stop here, as we said, because we're going to need moles of carbon, but we also need mass of carbon as well. So let's get that number. Well, let's just do the mass first to keep it simple. So we're going to use the atomic mass of carbon now to figure out how many grams of carbon there are. All right, so that gives us 0.238 grams of carbon. All right, so that's how many grams of carbon are in 0.871 grams of CO2. You could also do it with mass percent, but then you have to go through and calculate the mass percent of carbon and use that to convert grams of CO2 into grams of carbon. So it's really similar amount of work. If you prefer that, go ahead, but this is how I will typically do it. We'll do the same thing for hydrogen now. And remember, in a combustion analysis, all of the hydrogen in your compound that you burn ends up in water, H2O. So we measure out the mass of water, and it's given as 0.179. We're going to do the same thing. We're going to convert that to moles first. In this chapter, when in doubt, convert to moles. That's always a good way to do it. So the molar mass of H2O is 18.02, 2 hydrogens, which are 1.01, 1 oxygen, which is 16, so 18.02 is the molar mass of that. Now here's where we have to be a little bit careful. There's one small difference. If we look at the formula of H2O, there's a subscript of 2 by hydrogen. That means 1 mole of H2O has 2 moles of hydrogen. So we're trying to find the amount of hydrogen element that's in there. So there's 2 moles of hydrogen for every mole of H2O. Again, that comes directly from the chemical formula H2O. So we have to make sure we don't forget that step. And then we use the atomic mass of hydrogen to figure out how many grams that would be. So 1.008 grams of hydrogen in 1 mole. 0.0200 grams. All right, so again, a pretty small number, but we'll need that number later. And then, as we said, the only reason we need these masses is to figure out how much bromine is in the compound. Because when you burn the compound, and you have other elements in there besides carbon and hydrogen, those other elements are not going to be forming CO2 and water. If you have oxygen, the oxygen in your compound will go into CO2 and water, but it'll be divided up between the two. You're going to be adding oxygen that you burn it in. So for oxygen, you have to do the same thing. You can't figure out how much oxygen is present unless you do it by difference. So here the other element is bromine, so let's get the mass of that now. And for any other element besides carbon and hydrogen, again, you're going to find it by difference. So we burn 5.00 grams of the compound. Then we're going to subtract from that the mass of carbon that we found, which is 0.238. We're going to subtract from that the mass of hydrogen that we found, 0.0200. And whatever's left over is going to be our bromine. So that's the total mass of the compound. That's how much carbon there is. That's how much hydrogen there is. Everything else is what's left over, which is 4.74 grams of bromine. All right, so that's the mass of bromine. So in this series of steps, and you can start to see that these problems can be a little bit tedious, I'm not going to lie. In this series of steps, we've gotten the mass of each element. So now we're off to the races, because if we have the mass of each element, we know what we have to do now to find the empirical formula. We just need to convert the mass of each element into moles, okay? All right, so let's do those second steps of steps now. So for moles of carbon, we're basically going to just be undoing this last step here. We already got to moles of carbon in this conversion here, but we took it one step further to get mass. So we just need to undo that last step by dividing by the atomic mass. So we have that many grams of carbon that we found in the first step, and we divide by the atomic mass to get it into moles. So we get 0.0198 moles. For hydrogen, we had 0.0200 grams. This one we probably don't need to do the calculation in great level of detail because the atomic mass of hydrogen is basically 1. So moles and mass are essentially the same for hydrogen. So it's going to be 0.0198 again, but we could have just said it's 0.02, that's close enough. And then finally for the other element, which is bromine in this case, we found by difference that there was 4.74 grams of that element. And we're going to use the atomic mass of bromine, which is 79.9. 0.0593. All right, so those are the moles. Sorry, that should be moles, not grams. I wrote it wrong. All right, so that's the moles of each element, and now we just have to convert those to the simplest ratio to get the empirical formula. C 0.0198, H 0.0198, so those two are the same, and then Br 0.0593. This one we could probably do in our head, but if we divide all of them by 0.0198, the formula we get is CHBr3. All right, so 1 to 3 ratio. So it's more steps because we don't give you the masses or the moles of the elements directly, but once you get those, you just follow the rest of the process to get the empirical formula. All right, so any questions on combustion analysis? Okay, the one thing I want to point out that didn't come up in this problem, but it's important, is very often the other element, here it's bromine, but sometimes the other element in the compound will be oxygen. In that case, you still have to find it by difference. Because again, reviewing the combustion process, what you do is you take your compound and you burn it in the presence of O2. When you ever do a combustion reaction, it's burned in the presence of oxygen. So if you have oxygen in the compound, you're going to be adding oxygen from the air when you burn it, and then the oxygen is going to be distributed into the CO2 and the water. So you can't use those masses directly to figure out how much oxygen was there. You still have to do it by difference. So the mass of carbon can come from CO2, the mass of hydrogen comes from H2O, but if you have any oxygen, you also have to do it by difference, just like we did here for bromine. Mass of the compound, subtracting out carbon and hydrogen. Okay, so any questions before I move on? All right, so what we're going to talk about for the second half of today is now using moles in the context of chemical reactions. So we've used moles to talk about the composition of the compounds and in relationships between mass and moles and number of atoms and molecules. All that stuff we've talked about so far. Now we're going to move into a next major topic in this chapter, which is also going to come up again in chapter 6, which is what's called stoichiometry, which is going to be talking about the amounts of substances that are involved in chemical reactions. And again, the moles being the unit that's going to be most important for that. All right, so if we talk about a chemical equation, so when we have a chemical reaction, we're taking some combination of atoms and elements and compounds. They're reacting with each other, and they're forming some new combination of elements and or compounds. And so how do we represent that? We represent it with what's called a chemical equation. So a chemical equation consists of a few different aspects. So there's reactants, which are the elements or the compounds that are consumed during a reaction. So as the reaction is happening, these substances go away. So it means to be consumed. Oh, come on. Yeah, it's got to be I think I need to tell this guy to change his HDMI cable. All right, and then the products are the elements and or compounds that are formed. Now, it should be obvious from what we talked about at the beginning of the course that one of your reactants, at least one of your reactants and or one of your products must be a compound. You can't convert one element into another element, but you can convert elements into compounds or compounds into elements or compounds into different compounds. There's a lot of different possibilities. Now, the key aspect of a chemical equation that's going to be important for us in the context of what we're doing in this chapter are the coefficients. So these are going to be numbers in front of each formula or symbol. So formula if it's a compound or symbol if it's just an element. And they tell you the relative number of each of those that reacts in the reaction, that participates in the reaction. So it's going to be the number of atoms if it's an element, the number of molecules if it's a compound, or the more important way to interpret it is in terms of the number of moles of that substance that react. I'll call it substance, not species. That might confuse people. All right, and so it's important we can interpret it at either the molecular level or at the level of moles. So we could say that each coefficient tells you how many molecules or how many atoms of that substance are in the reaction, or because the number of atoms and the number of molecules are related to moles by Avogadro's number, those coefficients likewise tell you the relative number of each moles that are involved in that chemical reaction. And when we're writing out chemical equations and balancing them, which we're going to talk about next, we have to remember one of the first things we learn, which is the law of conservation of matter, which is that atoms are neither created nor destroyed during a chemical reaction. So however many of atoms you have on one side of the equation as your reactants, you're going to have that many as well in the products. So the amount of each atom in terms of its number of moles or number of atoms, however you want to think about it, and its identity is going to be the same on the reactant side of the equation and on the product side. So you're not going to create or destroy atoms during a chemical reaction. Okay? So let's talk about then, oh sorry, we have a question? Oh, that should be another word there, that tell you. Thank you. They tell you the number of atoms, molecules, or moles of each that are involved in a relative sense. So when we talk about balancing equations, we will usually do it with smallest whole number coefficients, but it doesn't have to be that way. You can have fractional coefficients, it's not technically wrong, and you can have coefficients that are not the smallest whole number, which again is not technically wrong, although the most common way to do it is with the smallest whole number coefficients that are possible, which then tells you the relative number of atoms, molecules, or moles. And these coefficients are mostly important in a relative sense. How does one coefficient compare to the other? So sometimes there's more than one way to balance an equation, and as long as there is a valid way of doing it, you'll be fine in terms of how you use those coefficients. All right, anything else before I move on? So let's talk about the steps for balancing chemical equations, balancing chemical reactions. So the first thing we do is we're going to put the reactants and the products on the correct side. I mean, sometimes we'll give you the equation without coefficients, and all you have to do is supply them. Other times we will describe the reaction to you. We'll say this reacts with that to form this and that other thing, and you have to make sure you arrange them properly. So reactants go on the left and products go on the right, so that's fairly simple. We read chemical equations left to right just like we read most things in the English language. So we're going to put reactants on the left and products on the right of our chemical equation with an arrow pointing from the reactants to the products to sort of separate the two. And then we have to figure out how to add the coefficients. And this is, in some cases, a little bit of an art form. It's not always a scientific way of doing this. We're going to learn in Chapter 6 about a few different reaction categories where balancing them has some tricks involved, and there's some processes you can follow to make sure they're easily balanced. In other cases, it's more of like a guess and check, trial and error approach. But there is some approaches you can take that help you with that, so you're not all over the place. So what I like to do is I like to find the most complex reactant or product, which is not always obvious which one you should designate as that, but we're talking about a reactant or product that has the most different atoms in the formula and the most number of atoms in the formula, however you want to think about it. So find something that's fairly complex and set that to 1. Set that coefficient to 1. And sometimes you have a choice. There's not always a right or wrong way to do this, but find something that's fairly complex in the chemical equation and set that coefficient to 1 and don't touch it until you absolutely need to. And then for the rest, you're going to adjust the coefficients on the other species to make sure then that the number of atoms is the same and the type of atoms is the same on both sides of the equation. So we're going to make sure the atoms balance, and when possible, we're going to use whole number coefficients. Normally in homework and test questions, if we're asking you to balance the reaction, and that's really the whole point of the problem, we will specify whole number coefficients to make sure that's clear. If you're just balancing it on your own as part of a larger problem, if you don't want to go to whole numbers, that's fine. You can use fractions. It's not the end of the world. But whole numbers are usually easier to deal with, and if we ask, we'll usually specify them. And then you check yourself. So you want to make sure that the number of atoms on each side of the arrow is the same. Number of atoms and the type, we don't change them to something else. And just so you're not confused about this if you see it, we're not really going to ask you to put these in normally yourself. They're just going to be shown to you. Sometimes the reactants and products indicate their state of matter as with a little parentheses to the right of that. So if you see S in parentheses, that means that reactant or product is a solid. If you see L, that means it's a liquid. Again, you guys don't have to really put these in yourself, but if they're there, I don't want you to be confused by them. A lot of times they're not going to be shown explicitly, but they will be sometimes. That's just what those mean. It doesn't change how you balance the equation. It just tells you the form of matter. We'll learn another one in Chapter 6 that's also important, another little parentheses that goes next to the reactant or product to tell you its form, but again, that's going to be there sometimes, but not always. Okay, so that's how we balance, and it's one of those things just like everything else in this course that you just have to practice and get comfortable with. So let's do some examples. So this is a combustion reaction. We're taking C2H6, which is called ethane, is one of the components of natural gas, not the most major component, but it's in there. And we're going to burn that with oxygen and form, as we said, carbon dioxide and water as the two products. Okay, that's a typical combustion reaction, same thing we talked about in the context of combustion analysis. So how do we balance this? All right, so we need to identify something that would be what we call the most complex substance, and I'm going to use C2H6 because most of the reactions and products have two different elements in them, but this has the most number. This has a total of 8 atoms in the formula. The rest are smaller coefficients. Let's set this to 1 to start. As I said, you don't have to do it this way, but it's always good to identify something that's fairly complex that you can set to 1, and then you're going to balance everything else off of that. Because if you're trying to change all the coefficients at the same time, you might adjust one coefficient and that messes up the other one. You have to go back and forth a million times. So set something to 1 ideally to start, and that's what I'm going to do here with C2H6. And then what you want to do is you want to find elements that only appear once on each side of the arrow and balance those first. Because if we look at oxygen, oxygen appears here as a reactant in O2, and it appears in both of our products. So balancing oxygen is going to be tough because there's a lot of different combinations of coefficients that will allow oxygen to be balanced on both sides. We have 3 things that involve oxygen. So let's start with an element that only appears once on each side of the arrow, and one of those is going to be carbon. So we have carbon here in the reactant, and carbon only appears in one product. So if we look at this here, we have C2H6 with a coefficient of 1. So that means we have 2 carbons on the left side. We also need to have 2 carbons on the right, and so the way we do that is put a coefficient of 2 in front of CO2. So now we have 2 carbons on each side. And then we can do the same thing for hydrogen. Hydrogen only appears once on the reactant side in C2H6, once in the product side in H2O. So at present, we have a coefficient of 1 in front of C2H6. There's 6 hydrogens then total on the left side. We need to have 6 on the right as well. Water has 2, so we need 3 waters to have a total of 6 hydrogens. So now carbon and hydrogen are balanced, and so we don't want to touch those coefficients anymore. We just have to figure out how much O2 we need to make sure that oxygen is also balanced. So on the right side of the equation, where we've already set the coefficients, for oxygen we have 2 times 2 from carbon dioxide, and then we have 3 times 1 from water. So we have 2 carbon dioxides that have 2 oxygens each, 3 waters that have 1 oxygen each, and that's going to be a total of 7 oxygens on the right. So we have 7 oxygens on the right, we need 7 on the left. How do we do that for O2? How do we make sure that there's 7 oxygens if it's in the form of O2? What coefficient should we use? Sorry? It'll be a fraction, that's right. So we can't do a whole number because that would always give us a whole number, that would always give us an even number of oxygen atoms. So if we want 7, we're going to use 7 over 2 or 3.5. All right, remember, you multiply the coefficient in front by the subscript in the formula to tell you how many of each atom there are. So if it's O2, if we have 7 over 2 or 3.5 of those, that's a total of 7 oxygens on the left as well. So this equation is technically balanced now, although as I said, we don't usually use fractional coefficients. So then what you're going to do is multiply every coefficient by whatever factor you need to get rid of the fractions. So here we have a fraction over 2, so we're going to multiply everything by 2 to get rid of that fraction there. But again, you have to do it for every single coefficient because this is already balanced. So if we change one coefficient by a factor, we have to change all of them by the same factor to keep it balanced. So 1 times 2 is 2, 7 halves times 2 is 7, 2 times 2 is 4, 3 times 2 is 6. So this is going to be our smallest whole number set of coefficients that balances this equation. All right, and again, we need oxygen last because it appears in both of our products. So if we check the different elements now and make sure that they're balanced. So on the left side and on the right side of the arrow, let's check them out, make sure they work. So on the left side for carbon, we have coefficient of 2 and then 2 carbons in the formula, so we have a total of 4 carbons. On the right side, we have a coefficient of 4 in front of CO2 with 1 carbon in the formula, so that's also 4. For hydrogen, we have 2 times 6 in that reactant, which is 12. 2 C2H6, 6 hydrogens each. And then the product side, we have 6 waters. So coefficient of 6, the formula has 2 hydrogens in it, so 6 times 2 is 12. So 12 hydrogens on each side. And then finally for oxygen, which is the last one we did, a little bit more complicated. On the left side, we have 7 O2s, so 7 times 2 is 14 oxygen atoms. And then on the right side, we have 4 CO2s, 4 times 2 for CO2, which is 8, and then 6 waters. 6 times 1 is 6, so 8 plus 6 is also 14. So all of these check out with each other. Carbon is the same on both sides, hydrogen is the same on both sides, oxygen is the same on both sides. Okay, so that's your sort of check you can do to make sure it's correct. If you trust yourself in the previous steps, you don't have to go through all that extra effort, but it is good to make sure that everything is balanced. All right, so questions on balancing equations. So we'll just do a few more, and if any questions pop up, just interrupt me. So let's start with this one here. So this is an example where we explain the reaction to you. We don't give it to you in terms of reactants and products. So Fe2O3 is the formula for rust. And as you probably know, it's formed by a reaction of iron and oxygen. So iron on the surface, oxygen in the air, they react to form rust. So we want to write a balanced chemical equation for the formation. All right, so again, this time we did not give you the reactants and products directly. So we're reacting iron and O2. So iron has a formula Fe from the periodic table. It's just an element. And then oxygen gas has a formula of O2. So those are going to be our two reactants, Fe and O2. And they're forming, so whatever you're forming is the product, and they're forming Fe2O3. So this one, once we have the reactants and products arranged correctly, should not be terribly difficult to balance. Again, we're going to find one species that's the most complex and set it to 1. So this product here has 2 elements in it. Everything else is just a single element, so we'll set that to 1 to start with. So now we have 2 Fe, 2 irons on the right side. We also need 2 on the left, so we put a coefficient of 2 there. Oxygen, 1 times 3, we have 3 oxygens on the right. So if we want to have 3 on the left, same argument as last time, we need a fractional coefficient of 3 over 2. All right, so this equation is balanced, but if we asked you for whole numbers, we have to again multiply by 2 to get rid of the fraction. Usually, I don't want to say always, but usually your fractions are going to be, if anything, something over 2. It's not typically going to be more complicated than that, especially if you follow a relatively logical approach for balancing. So usually it'll be, if anything, a fraction over 2. You just have to double everything to get rid of it. So if we double everything, we get that 2 becomes a 4 for Fe. 3 halves times 2 is 3. And then on the product side, we get 1 times 2 is going to be 2 Fe2O3. And so now if we check the balancing, we have 4 Fe's on each side, 4 over here, 2 times 2 over there, and we have 6 oxygens, 3 times 2 or 2 times 3, 6 on both sides. Everything works out. All right, so that one was not terribly difficult to balance. It's just that time we had to make sure we arranged the reactants and products correctly before we could start putting in the coefficients. So any problems with that? All right, the last one I'll do is, it looks complicated in writing, although it's actually, as you'll see, not being that bad. So this compound here, cesium-4, rhenium-6, selenium-8, I6, is formed by heating rhenium, selenium, cesium iodide, and I2 to 800 degrees Celsius for 4 days. Now, why did I pick this very random and specific example? Well, this is the first compound ever made in a research lab, so it has a very special place in my heart. They say you always remember your first kiss, but you also remember your first chemical reaction. This is mine. So this is the compound, and that's how you make it. You do it in a sealed tube, and it's kind of a neat substance. It glows bright red when it's done. It's pretty nice. So we're going to write the balanced chemical equation for forming this, and then the way I set up this problem is just sort of a typical way you might see it in Blackboard. There's not really any value in doing this, but again, with Blackboard, we can't have you write out full chemical equations. That's too much, right? So we'll usually just ask you about something about the coefficients as part of the problem. So here what we want you to do is we want to sum the coefficients on the reactant side when you're balancing with smallest whole numbers. And that would be the answer you to put into Blackboard. Again, there's not really any value in that number. It's just the way that we could ask it in Blackboard to format it in an appropriate way for that online platform. So what we have is we have 4 reactants this time: rhenium, selenium, cesium iodide. I should probably do this a little bit lower, I think. Yeah, let's do it lower so I don't run out of room. Then the last reactant is going to be I2, and the product is this monstrosity here, CS4, rhenium-6. So basically one of the first things I had to do when I started working in a research lab second year of college was figure out how to balance this equation and then figure out how much of each of the reactants I need to make the product that I wanted. So we're going to get to that in a second. We don't know how to do that yet. But first step was balancing the equation, so we're going to start with that. Now I think it's pretty obvious which substance here should be set as our most complex with a coefficient of 1. I don't think there's any doubt that this is going to be this product here. So we'll leave that as 1, then we'll balance everything else off of that. So again, we want to find the elements that appear only once on the reactants and product side. Those are the most straightforward to balance. So iodine, which is our last element in the formula, appears in both I2 and CSI. So we don't want to do that one first, because again, we don't know which combination of coefficients we need to keep iodine balanced. That's not a good one to start with. But the rest, cesium, rhenium, selenium, they all appear just once in the product and once on the reactant side as well. So for cesium, this formula has 4 cesiums, so we need to have 4 on the reactant side as well. Our formula has 6 rheniums, Re6, so we need 6 over there as well. So we put a coefficient of 6. And then selenium, there's 8, and so we need a coefficient of 8. So now we've gotten the first 3 elements in the formula balanced, cesium, rhenium, selenium, and we just have to make sure that iodine is also balanced. So our product has 6 iodines in it. And so far we've added 4 from CSI. So we have 4 cesium iodides, and then if we have just 1 I2, that will give us the correct number of iodines on both sides. Okay, so it's 6 on the product side, 4 that we'd already had from CSI to balance cesium, 1 more I2 gives us a total of 6 iodines. So it's a little bit more complicated to think about, but it's still the same approach. Make sure all the elements are balanced. And then what this asks for is the sum of the coefficients on the reactant side. All right, so the reactant side is the left side. It's those 4 things there, so it's going to be 6 plus 8 plus 4. When you're doing this, remember that we don't usually explicitly write coefficients of 1. I often do it when I'm balancing equations so that I keep track of it, but at the same time, these coefficients of 1 won't really actually show up. We have to make sure we don't forget about it. So the more standard way to write this would be without coefficients on those, because coefficients of 1 are usually left off, but we still can't forget about that it's there. So we still have to add that 1 from I2, even though it's not going to be necessarily explicitly shown in the final form of the equation. And so that gives us a total of 19 when we add all those up. So don't forget about coefficients of 1. They're still there. They're just not usually written explicitly in balanced equations. All right, any questions on balancing? All right, so the last thing we're going to cover with whatever time we have left today, we probably won't finish everything that I had planned, but that's okay, is moving into what's called stoichiometry. So, you hate stoichiometry? Haven't even learned it yet.
Okay, I did that like it.
All right, well, I'll make sure you like it better this time, all right? All right, so what stoichiometry involves is going to be talking about amounts of substances in a chemical reaction. So the amounts of reactants, the amounts of product that form, and how they're all related to each other. All right, so we're going to define it in this way for now. It's going to be calculating amounts of reactants and or products. So you can do it for any substance in the reaction. That are involved in a chemical reaction. And the key thing that we need for stoichiometry, there's going to be several variations. We're going to learn some of them in this chapter, more of them in the next chapter. A lot of different variations on stoichiometry problems, but the key is going to be what are called mole ratios. And these are going to come from the coefficients of the balanced equation. So, balancing chemical equations is not just a one-off topic that we're going to be done with. It's exceptionally important for what we're doing now in stoichiometry because the coefficients tell us the ratio of the moles of each substance that's involved in the reaction. So any stoichiometry problem starts with a balanced chemical equation. We either give it to you or you have to produce it yourself. And those coefficients tell us the relative numbers of moles of each substance that are involved. So we said that coefficients can be interpreted at the microscopic level, number of atoms or number of molecules involved, but the more important and more common way is to interpret them as the number of moles of each substance in the reaction. All right, so what we're going to do is in sort of abstract form is let's say we have a chemical equation, 3A plus 2B goes to 4D. Obviously, A, B, and D are not clearly defined in this case, but the important part is the coefficients. And what we can do with those coefficients is write ratios of reactants and products that are involved in the chemical reaction and use those ratios as conversion factors to convert an amount of one substance in the reaction into an amount of another substance that's involved in that same reaction. So we could write this one, any combination of the coefficients. So 3 moles of A reacts with 2 moles of B. We can write that ratio or flip it to get the relationship between B and A. We can write it as a ratio and it's going to convert between those two substances. Or we have a coefficient of 3 in front of A, so 3 moles of A reacts to form 4 moles of D. So if we want to know the relationship between reactant A and product D, we use that mole ratio from the coefficients to convert one of them into another. Or we can do it for the other reactant. So if we have 2 moles of B reacting, we form 4 moles of D, and so on. There's all these different combinations you can write with different combinations of reactants or products written in with either one in the numerator, either one in the denominator. And these are all going to be used as conversion factors. Again, to convert one amount of substance into an amount of a different substance. All right, and so that's going to be the key idea with stoichiometry. So typically what you want to do in stoichiometry then, the first thing you want to do is find the moles of the substance, because once you have moles of a substance, you can use the coefficients to convert that into moles of a different substance. That's really the main point of stoichiometry. So let's talk about then, in abstract form at least, the process for stoichiometry. So at least in this chapter, the most common type of stoichiometry problem is we're going to give you the mass of one substance in a reaction. I'll call it substance A. And we're going to ask you to find out what mass of a second substance, which I'll call B, is involved in the reaction. So again, A and B can both be reactants. They can both be products. One can be a reactant, one can be a product. It's just two different substances in the chemical reaction. And we figure out, okay, we have this much mass of substance A that's involved in the reaction. How much mass of substance B would be involved in that same reaction? But we should recognize that there's no direct conversion between these because chemical equations are not written in terms of mass, they're written in terms of moles. So the process we usually follow then is we're going to use the molar mass of A, which I'll abbreviate as MW, is going to be used to convert the mass of A into the moles. And then once we have moles of substance A, we can use the reaction coefficients to convert moles of substance A into moles of substance B. And we can go in either direction, obviously. So if we have coefficients then, what we call the stoichiometric coefficients, those coefficients from the balanced equation, those allow us to convert the moles of substance A into the moles of B, or vice versa. And then once we have the moles of substance B, it's going to be related to its mass by the molar mass of B. All right, so it's a sort of a 1, 2, 3 step process to go from mass of one substance to mass of another. Convert to moles first, use coefficients to convert into the moles of other substance, and then use its molar mass to get back into a mass unit. Now there is one other slight variation that I'll point out, but it's not going to be as common. But we also have Avogadro's number. So what we can do is use Avogadro's number to convert the moles of one substance into the number of atoms or molecules of that substance. Or we can do the same thing for the other substance, use Avogadro's number to convert its moles into the number of atoms or molecules. All right, so in reality what we have is, we have now two relationships involving moles, mass to moles, which involves atomic or molar masses, and then we have moles to number of atoms or molecules, which is Avogadro's number. Those are going to be typically used in combination with this key step here where we're using reaction coefficients to convert one substance into another in terms of their molar amounts. Okay, so that's kind of the abstract process for stoichiometry. So let's just do one example to close off. We'll do the rest next time to sort of solidify this. one or two examples depending on how much time we have. So let's say we have this reaction here. This is dissolving gold in an acid solution called aqua regia. And we want to know how many molecules of water are formed when 2.56 grams of gold is completely converted. So basically we're reacting all of our gold, 2.56, converting it into these products. We want to know how much of the water is formed in terms of number of molecules. All right, so again, for stoichiometry problems, I like to always start with what we're looking for. We're looking for molecules of water. All right, so that's what we're looking for is molecules of water. And what we're given as a starting point is the mass of one of our reactants or products, in this case, our reactant gold. So that's our starting point. So we always start out with something that we're given, which is 2.56 grams of gold. In stoichiometry problems, when in doubt, and really almost every time, your first step is going to be to convert into moles. Right? So we can't do anything with stoichiometry until we're in moles. So we know that to convert grams into moles, we just have to divide by the atomic mass. In this case, it's an element. So we have to go to the periodic table for that. Gold is here, 196.97. Okay, so that's the atomic mass of gold. All right, so we're going to divide by that number. And that gives us into moles of gold. What we're looking for is molecules of water, so we're still not there yet. Once we have moles of one substance, we can convert it into the moles of the other substance using the coefficients. So we're looking for an amount of water, which is a different substance, so now we can use the coefficients to convert between those two. So make sure we write those in the correct order. Let's make sure our units are kept close track of. So we want moles of gold to cancel, and we want moles of water to be what we're going into. So if we want moles of gold to cancel, we need its coefficient in the denominator. Gold doesn't have a coefficient, but remember that means it's actually 1. And then for water, the coefficient is 2, so that's going to go up here with water. All right, so moles of gold cancel out. Moles of water is what we're left with. But again, we're not looking for moles of water. We're looking for the number of water molecules. And so for that, we multiply by Avogadro's number. All right, so we're looking for molecules of water. And what we want is moles of water in the denominator. All right, and so if we want to convert number of moles and number of molecules, we use Avogadro's number, 6.02 times 10 to the 23rd, water molecules in 1 mole. So that cancels out moles and gets us to the unit we're looking for, which is number of water molecules, which comes out to 1.56 times 10 to the 22nd molecules. All right, so as I said, it's not particularly common or useful to figure out how many atoms or molecules are involved in a chemical reaction, but here we did that, and that is possible by using the first relationship for moles we learned, which is Avogadro's number. So I think I'll stop there. I'll do the next example at the beginning of next time, which is a more typical mass-to-mass type of problem. So we'll start with that, and we'll go into some other details about stoichiometry as we move forward.